Welcome to the AP Chemistry video podcast series on voltaic cells, electrochemistry, all that stuff. How's that for an introduction? We're looking at following up our podcast on voltaic cells with a series, three-part series on how to use the Nernst equation in calculations. So, welcome. One of the things you've experienced in life, if in no other place than with your calculator, has been that the battery runs down. Cell phones, all those types of devices that we're used to using batteries in, we have to either recharge them or get new batteries depending on the battery type. So cell voltage changes, and cell voltage changes as the cell discharges. Concentrations of the reactants and products change, and voltage is dependent on the concentrations of the reactants and products. We can calculate the voltage at any point in time using the Nernst equation. So that's what we are looking to do. We're going to look at several versions of the Nernst equation. Here's the complicated version, and Q, remember from our equilibrium studies, is the reaction quotient. If the reaction is at equilibrium, then Q is equal to K. When a battery, in a battery system or a voltaic cell system, if the reaction is at equilibrium, there's no more cell discharge, or there's no more electron flow, net electron flow taking place, so you don't get any activity that can be measured. So the energy of the cell is equal to the standard energy of the cell, which is a calculated value that we did when we studied voltaic cells, minus RT over NF times the natural log of Q. Now, R is the universal gas constant, but in this case, R is going to be related as a thermodynamic quantity. So we will use the value for R as 8.31 joules per mole of reaction times Kelvin. The temperature is at 298.15 Kelvin. N represents the mole of electrons per mole of reaction, and you'll see how that works as we go on. And then F is Faraday's constant, and that is equal to 96,500 joules per volt times mole of electrons. It would be a good idea for you to write down this equation and what these values represent. Now would be a good time. Now let's look at a simplification of the Nernst equation. Here we have E of the cell is equal to E of the cell under standard conditions minus 2.303 times RT over NF times the log of Q. Notice we have converted from a natural log to a base 10 log. And so the other simplification here is we want to take our RT over F, that's the 8.31 joules per mole times Kelvin times 298.15 Kelvin, divide that by 96,500 joules per volt times mole of electrons, and what we get is a value of 0.0257, and that number will help us immensely in terms of our simplification of this equation, as you'll see on the next slide. So as we continue to simplify, we see our E of the cell is equal to the E of the cell under standard conditions minus the 2.303 times the factor of 0.0257 volts over N times the log of Q. 2.303 times 0.0257 is equal to 0.0592. So our very simplified version is E of the cell is equal to E0 of the cell, or the cell under standard conditions, minus 0.0592 volts over N times the log of Q. What we arrive at is a form of the Nernst equation that is very usable. So this you should have written down in your notes. This would be very helpful to you as you approach these type of problems that involve the Nernst equation. E of the cell is equal to E of the cell under standard conditions minus 0.0592 volts over N, which is the number of moles of electrons per mole of reaction, times the log of Q. So use this version when you solve for E of the cell under non-standard conditions. Remember, non-standard conditions means that you have concentrations other than 1 mole per liter, or you're at a pressure other than 1 atmosphere, or you're at a temperature different than 298.15 Kelvin. Let's look at a problem. We have a voltaic cell with a nickel 2 plus, and cobalt 2 plus half cells. Has the following initial concentrations. The nickel 2 plus is 0.80 moles per liter, and the cobalt 2 plus is 0.20 moles per liter. We want to know A, what is the initial E of the cell, B, what is the concentration of the nickel 2 plus when E of the cell is equal to 0.03 volts, and C, what are the equilibrium concentrations of the ions. In the rest of this podcast, we're going to address part A. The second part of the Nernst equation podcast will deal with part B, and finally the third part will deal with part C. The solutions to these will look rather long, and that's why these podcasts are going to be split up. So if you would go ahead and write the problem down, and you can even try to solve it and then come back and see if your solution matches mine. So pause the podcast as you need to, and then we'll move on. Before we can solve for parts A, B, or C, we need to know the energy of the cell under standard conditions. So let's look at the two standard reduction potentials and the equations that accompany them. Nickel 2 plus 2 electrons yields nickel, and we see that the standard reduction potential there is minus 0.24 volts. Cobalt 2 plus 2 electrons yielding cobalt metal, the standard reduction potential is minus 0.28 volts. The half reaction with cobalt is less positive, so we'll choose that half cell to be the anode. So again, looking at these two reactions, in order to find E of the cell, we have to make sure that we arrange this so that it's a spontaneous reaction, and so we make the half cell with the less positive standard reduction potential to be the anode, or where oxidation will take place. Since the half reaction with cobalt is less positive, we will flip that half cell, reverse it, so that cobalt yields cobalt 2 plus 2 electrons, which is cobalt being oxidized. And then the standard reduction potential, we change that to a standard oxidation potential by reversing the sign. So since the standard reduction potential was minus 0.28 volts, the standard oxidation potential would be plus 0.28 volts. Now that we have the half cells arranged as both a reduction half cell and an oxidation half cell, we can find the E of the cell under standard conditions by adding the standard reduction potential of the nickel half cell to the standard oxidation potential of the cobalt half cell. So that would be the minus 0.24 volts for the reduction potential plus 0.28 volts for the oxidation potential. When we add those together, we get a positive 0.04 volts. The alternative method would be to take the standard reduction potential at the cathode, which is 0.24 volts, minus the standard reduction potential at the anode, which is negative 0.28 volts. So 0.24 volts minus negative 0.28 volts gives us the energy of the cell under standard conditions as plus 0.04 volts. Next, we want to add the half reactions together to get the net reaction. So we have our nickel 2 plus 2 electrons yields nickel, and our cobalt yielding cobalt 2 plus 2 electrons. When we add these two half reactions together, the two electrons will cancel, So we'll get nickel 2 plus aqueous plus cobalt solid will yield nickel solid plus cobalt 2 plus. And we learned in class a cell notation for that. And what we do is we put the anode to the left, the nickel to the right. And so what we have is cobalt solid going to cobalt 2 plus, and then our two lines representing the salt bridge, then nickel 2 plus going to nickel. The leftward species is what's on the reactant side of the equation. The rightward species in each of these half cells is what is on the product side of the equation, and that's going to be important to us when we go to find the value of Q. Well, we want to find the value of Q, so we look at our equation, and we know that whenever we wrote equilibrium constant expressions, we always put the concentration of the products over the concentration of the reactants. In this equation, we won't include either solid, so the cobalt solid, nickel solid, those won't be included. So what we're going to do is make Q equal to the concentration of our cobalt 2 plus, which is our product, and have that divided by the molar concentration of our nickel 2 plus, which is our reactant. And so we're going to have the 0.2 moles per liter for the cobalt 2 plus on top, divided by the 0.8 moles per liter of the nickel 2 plus on the bottom of our expression. And when we do the math on that, we have Q equal to 0.25. Let's look at our data table to solve for E of the cell here. We know that N is equal to our 2 moles of electrons. We know that from the energy of the cell calculations, because the nickel needs 2 electrons, Ni2 plus needs 2 moles of electrons per mole of Ni2 plus to be reduced to nickel. And when cobalt is oxidized in this reaction, it's going from cobalt to cobalt 2 plus. So there are 2 moles of electrons for every mole of cobalt that is oxidized. The number of moles of electrons for both half reactions are equal, so they're already balanced. We don't have to do anything else to that. Q we calculated as 0.25. Thus, E of the cell under standard conditions is 0.04 volts, and E of the cell is what we're looking for, so we put a question mark there. So our base equation on this is the energy of the cell is equal to the energy of the cell under standard conditions minus our 0.592 volts divided by N times the log of Q. For some reason, I decided to give you another look at our base equation, so I hope you enjoy that. Have it written down as we continue to solve this. And here is our working equation where we're going to put in our actual values from our data table. E of the cell is equal to 0.04 volts minus 0.0592 volts divided by 2 moles of electrons times the log of 0.25. When we do that, we get a final value of 0.05 volts. So the E of the cell initial under the conditions of a 0.20 mole per liter cobalt 2 plus solution and a 0.80 moles per liter nickel 2 plus solution is 0.05 volts. Well, we've come to the end of our Nernst equation video podcast part 1, where we dealt with how to solve part A of the sample problem using the Nernst equation. I want to leave you with a quote from Benjamin Disraeli, a great British statesman. Desperation is sometimes as powerful an inspirer as genius. Thanks.